All right. Hi, folks. I'm here again with a guest, special guest again, Lukasz. And yeah, we wanted to talk a little bit about different types of analysis types, right? And yeah, so we have encountered some of them during our career. And we want to just walk a little bit through, and also your experience. If you have any experience with that and comments, please let us know, just to know in advance. Yeah, and we'll just have a little bit of a conversation. So, hi Lukasz, how are you?
Hey man, it's a pleasure to be here again.
Yeah, same thing.
Yeah, it will be fun, I'm sure.
Yeah, definitely. All right, so we both enjoyed our cups of tea, or are enjoying our cups of tea. I told you that I will show that to you. So my little cup of tea, like green tea. Yeah. And yeah, let's start with the linear. Let's start with some easy linear simulation, right?
I think that starting easy is a good choice. Like,
Better,
I would
yeah.
be super surprised if most people wouldn't start with linear analysis in FEA.
Yeah.
And I actually didn't, but it was mostly because I had no idea what I'm doing when I was starting. So
same thing.
I think that we should also say that we will be mostly talking about structural analysis, because, like, technically speaking, you could use FEA for a lot of various things. And
yes.
we'll be interested in the analysis that would allow you to design something, let's say.
Yes.
So without a doubt, the linear analysis would be first. And I think that it will get easier to talk about them as we progress toward the more complex ones.
Yeah.
Because usually that's the case, that the simpler the question you ask, the more difficult the answer will be. But for linear analysis, we should say that it's linear static analysis. And by linear, I mean that we won't consider nonlinear material, nonlinear geometry. Someone may argue that contact is linear or nonlinear. I hate the discussion myself, to be honest. But for now, let's say we're like out of it.
Yes.
We're not using contact. And static means that there is no vibration, no inertia effects. Nothing happens in time.
Yeah.
It's just somewhere in a space, you're doing the analysis. So if you think of designing a steel building, a ship, in many ways, like a plane or a rocket, whatever, this would be like the very entry-level thing you can do to it. So you have a model, you support it, you load it, you press play.
Yes.
And that would be the analysis. And at the beginning, I think that one could say also that I've read in one of the Nathan's books that there is an estimate that 80 to 90% of worldwide analysis done in FEA would be actually linear static analysis.
Yeah.
And this shows that without a doubt, that's like the most popular tool out there, for sure.
Yeah, definitely. Yeah, it's also the most, the cheapest one, right? So speaking of computer power, it's just cheap.
You can make linear FEA on your cell phone.
Yeah.
Most likely. In like real life. So while it's super popular, I wouldn't necessarily rate it as the best.
No. Yeah.
Clearly, because it would be super popular and the best, nobody would ever bother doing anything else.
Yes,
really.
sure.
And with linear analysis, you would very quickly encounter few problems you won't be really able to solve. And the most famous one, without a doubt, would be that you get stresses higher than yield if you design something from metals, because stress concentrations are crazy in linear statics. And whatever shape discontinuity you have, and you always have those, like a stiffness, something is like with an opening, whatever you will get. Yeah, the stress concentrations there will be very difficult, very high. And then, of course, if you want to design something with linear static, you would expect that there is some value of stress that you are willing to accept, and then the rest, higher values, are not acceptable. And this limit can be a lot of different things depending on the industry, material, or whatnot. But the idea is the same. As soon as I get this much of stress, thing breaks. The problem is that because of the limitations of linear FEA, or maybe even FEA in general, you will reach this value in a very small area very, very quickly. Under the loads, you would normally assume that shouldn't cause any problem. Heck, you can build the part, Load it with this load, and there
Yes.
will be no problem.
Yes.
And the most magical question of linear FEA would be, how much of this extra stress beyond what I'm willing to accept can I ignore? And there are like shamanic rules, and like FEA specialists divide into different tribes that have ideas of how much you can ignore and when. And you can try to classify what will be ignored and try to assess it somehow. But realistically, that's the problem of the method itself, that you don't have any plastic redistributions there. And there are situations where you won't have, like if you're designing a glass structure and you get the peak stress, that's a serious trouble, because glass do not redistribute stress in any meaningful way. It will just break. Right?
Yeah.
But as soon as you enter into like more robust materials, let's say, mostly metals really, then those materials can help you a lot with saving your life by pushing the stress outward. And in linear analysis, you just don't get it. So that
don't
would be
get an answer.
the biggest issue.
Yeah.
Yeah. And the second one is something that people are rarely aware of, and that would be stability. Because you can destroy something even though the stress did not even get close to what you are willing to accept.
Yes.
Because if something is very long, very thin, you start to compress it, it will just bend out of shape and everything goes south. And somehow when I talk about fatigue, engineers instantly know what fatigue is. Everybody is like careful about fatigue. So like maybe stresses aren't as high as yield or whatever limit I am willing to accept, but I still have to pay attention to fatigue, because you can do this in a linear way in some sense. Fatigue is manageable in linear analysis. You just check the differences, if maximal stress, minimal stress in each cycle, and you can do something with this information from linear analysis. And when you do linear stress analysis, the stability is just not there. So you can easily calculate a structure that already died and be blissfully unaware of it. So that's also a drawback, but to me it's the bigger one, because I would rather have problems that I know that I have them. So if I get stresses higher than yield, at least I know that there is a problem I have to fix. But if we would make like a popularity contest of what is the biggest problem in FEA, I'm absolutely certain that the stress is higher than yield would win with stability issues way, like by a landslide.
Yeah, it's the first thing you see. And also, talking from a different side, when you talk about linear static, first thing what comes to my mind is that you have to make sure that the real world can be simplified as this. And this is in most cases that's not the case, or rarely it's the case. And as you said, also this stress concentrations. I mean, you could have a part which is so minimally loaded that it has no really any issue with it, and you could go with a linear stress calculation and simulation and pass it through. But often you go on the boundary because you want to make it lighter, you want to increase your performance, whatever, and you will decrease the amount of material you use, and that brings you to the boundary of what your part can have and endure. And I just recently started digging a little bit deeper into fatigue, because that was not so much on my priority list until now. And I uncovered something with the fatigue scaling, for example. So you have a linear analysis and you get the stresses, and then you have a load cycle, and then you do rain flow analysis over it, and then you can estimate the damage and stuff. That's pretty helpful. And it's a different kind of simulation than the just typical linear stress simulation you're doing. And to be aware of it is, I mean, that's the major thing here, to just see. And I think that's also what we want to contribute with this discussion here, is that you're aware of what simulation types are there. And there's a lot. So if you have linear,
as you said,
sure.
I would still say that everything connected with fatigue, especially if you're doing like high cycle fatigue stuff, like the classical fatigue, I would still classify as linear stress analysis. You're not really worried about nonlinear effects mostly in those, right? But still, it's like a completely separate kingdom within this small group.
Right. And you could be unaware of it because you just have your static analysis in whatever preprocessor you want to use, and you just solve that and see your stresses, and then you say, all right, it's fine. But maybe it isn't. So to take fatigue into account is a major thing. Definitely.
Yeah, I would say that it's just, to someone who's unaware of it,
Yeah.
fatigue is just as dangerous as buckling, really. It only depends on what you are trying to solve, because some problems will be prone to fatigue issues.
Yes.
Different things will be prone to buckling issues, but both of those can beautifully catch you off guard without any warning whatsoever. You just did your analysis, you think everything's fine, and suddenly you're in a place you didn't expect to find yourself in.
Yeah, right. Then it breaks. Yeah, buckling, completely different thing, right? So we have now linear and buckling. Yeah.
That's actually wonderful, because, to me, engineering in general as an art is a fluid thing, and you're trying to just solve the problems you are aware of with the tools you have at hand. And this division between linear, non-linear, buckling, not buckling, whatever, it's like, imagine a river that you try to put into several buckets, and each bucket of water will be called differently because there are so many problems in the engineering world, right?
Yes.
But in fact, this is a river and everything is mixed together. So when it comes to buckling, we actually have an algorithm that's called linear bifurcation analysis. So calling it nonlinear in a sense is a cheat, but it's not necessarily linear in a way that you would think.
Yeah.
Because like when you do linear stress analysis, it actually produces an outcome an engineer would understand in a way that you can check what the stress is, what the deformation is, how your model behaved.
Yeah.
And when you're doing linear bifurcation, which is oftentimes called linear buckling, what you would get is actually a super crazy artificial shape that shows you how your structure will fail due to buckling in an elastic manner. And the only realistic outcome you will get is a single number, a single digit called eigenvalue. That would be like critical load multiplier to those of you who used Eurocode terminology. The idea is you applied load, and this number tells you what would be the multiplier for this load to reach failure. So if you have a model and you apply 1 kilonewton of load, and the multiplier is 100, this means that 100 kilonewtons fail your model due to elastic buckling.
Yes.
And on the other hand, if you would, in the same model, apply 100 kilonewtons, the multiplier will be 1, but the answer is still the same because it's load times the multiplier.
Right.
So you can do crazy stuff with this from
Definitely. Definitely. No, I was talking about it's different because it's not really a... how should I say? It's more like a modal simulation where you find perturbations
it's
of
super
your
esoteric,
matrix.
really.
Yeah.
Because when you see the outcome on a screen, the deformations make very little sense. The stresses make no sense at all.
Yeah,
the
you cannot use the stress
real
values.
Outcome is the shape.
It's the shape,
more or less.
Yeah.
And then this magical multiplier.
Yeah.
And this can caught people off guard because they will be trying to assess the values they get from this analysis. That's a pointless exercise. And I feel that this analysis, sadly, is just as overused as linear stress. I mean, if you would be solving simple beam structures and you have buckling, maybe lateral torsional buckling, and you have 7 degrees of freedom, or you model things with plates, if this would be like beams we're talking about, those would actually behave decently with linear
so
buckling.
you could use it for cranes, for example.
The buckling value you will get for those is reasonable. But that's not because linear buckling is so great. That's because beams are very nicely codified. Because what people get really wrongly is that linear buckling is not the capacity. When the linear buckling says, you need to increase your load multiplying with 1.2 critical multiplier. So everybody thinks, I have 20% of capacity
safety,
extra. This is not how it works. Because what you actually get is in ideal world, when nothing wrong can happen, everything is perfect
geometry.
This would be the perfect outcome. This would be called critical capacity in Eurocode. So like Euler buckling, the Euler's force is not the capacity due to buckling, it's the perfect ideal capacity of ideally elastic buckling of this perfect representation of an imperfect system. And the real capacity, even for beams, would be like 2-3 times lower.
Yeah.
So you would be expecting a multiplier of 2, maybe 3, to be kind of happy. But what I've meant is that this works with beams because codes like Euro codes and others, I'm sure as well, provide you with the simple or relatively simple equations that allow you to take that into account. So you make linear buckling allows you to calculate a critical force or critical moment depending on the load you applied in your beam. And then there is like 1-2 equations. So you input the critical moment into one of them, you get slenderness, then you calculate the capacity, and bam, you have the real capacity. It will be always lower than the critical.
Yeah, sure.
Oftentimes very much lower.
Yeah.
The reduction factor due to buckling can be easily like 0.3, 0.4 in a reasonably designed beam element. Structural steel, I mean.
Yeah.
But still, this is perfectly usable. You can analyze a very big steel building using linear buckling. Nobody would say that that's a stupid idea.
Yeah.
The problems start to come when people do plate structures.
Shells
like
and stuff. Yeah.
welded from plates, like big filters and God forbid shell structures.
Yeah.
And then suddenly you are trying to approach much more complicated phenomenon using the same simplified tools. But while linear buckling is never the answer, there are no friendly equations for plate and shell structures that you could use. So for beams, it was take your critical load, critical force, critical moment, put it into equation, compute 2 numbers. You can do a very simple Excel sheet that does it. And ta-da, you have the capacity. There are no equations for shell and plate structures. So
let me wait in on that.
Assume,
let's just say that if you would take these imperfections into account, like for a beam structure, like you would do some imperfections on that, and then you would also do your linear buckling. Would that be a way of calculating the real capacity more precisely for beams? For sure,
no.
But
well,
and for shell?
The problem with that would be that imperfections kind of have two things. The first one would be if you bend something and compress it, you get a second order bending in the element, and you have it. And that linear buckling would actually see. But this is not the biggest problem with imperfections. The biggest problem is that as you have this extra bending bends your element even further, making the imperfection even bigger. And then you compress again, and effectively you are wondering, will this stop? So the incremental increase in imperfection, will it stop at some point and this will be stable, or will it cycle to death and it will fail? And this is something linear buckling just cannot see. The magic of imperfections is that you are using nonlinear geometry to kind of like predict while you're running the analysis if this
load
stops, and linear buckling just can't. So I think that in my experience, using imperfections in linear buckling is a futile exercise because it won't provide you with the information that you need at the cost of extra labor. So you're not gaining anything really by doing this because it's still not a quote unquote correct answer. It's just a weird answer. And while if you make a perfect model with linear buckling, you can input the digits into the equations, at least in beam structures. If you do linear buckling with imperfections, that become awkward. Like you did something, but like nobody knows really what to do with this because that's not what you should aim for. And I would say that
let's say we have a different thing. We will do a linear buckling, take the shape of a buckling mode, apply that as a scaling factor of your model, do the imperfections like that, like pre-deform it, and then apply the loads for linear subcase again and see how the stresses behave. Would that be a thing to consider for imperfections?
If you would do a linear run for the second run, you're still missing on a lot of stuff. You need nonlinear geometry for this to work.
Sure.
It would change the outcome. You would kind of see a different outcome, obviously, right?
Yeah.
But it would be like first order outcome. So you would miss a lot of the bad stuff that could potentially happen. And that would be, if the stability would be a real issue, you wouldn't still, in many cases, you wouldn't still detect the problem.
Okay.
Because it's in the increase of the imperfection as the load that is applied.
and you
That's
just
where
have
the
one
things fail.
iteration.
And you just don't have it.
Yeah, right. Okay.
So-
Yeah, it's tough.
Well, I guess, yeah, it is. It is because people think, for better or worse, often that there must be a magic number that makes the problems go away. You know, that if I calculate nonlinear buckling and the number is 3, 5, 7, 10, everything will be fine from now on. But this is not how it works, because I've seen shells that had like multiplier of 4 or 5 and failed.
Okay.
And I see beams that had multiplier of 2 and were perfectly fine.
Yeah.
There is no magic number to linear buckling. It depends on the problem you're solving. And while if you would solve thousands of the same models, from experience you can derive something like, if I'm solving the same thing over and over and I get a buckling multiplier of this much, I will be okay. That's reasonable. But there are no general rules. You would have to really be careful about who tells you what's the limit and how
Okay.
they derived it, because
Yeah.
it would have to be specifically tailored to whatever you're doing. And honestly, nobody is willing to make the effort to do this. It's way more effective to actually do nonlinear FEA and simply do it correctly for every application, rather than writing huge, thick books of, if you're solving this or that, the multiplier should be this much, because that would be such an insane amount of work that it's beyond crazy.
I think that's also a little bit of history here, because we were not always able to do nonlinear analysis, and in the times where you had no other measure to just make assumptions from your linear calculations. But let's step into the nonlinear territory. Yeah. What kind of different sources of nonlinear? We talked about linear geometry. Let's first tell. What's that, and what other sources do we have?
So nonlinear geometry would be the thing that makes string work. If you would tie a string on two hooks on two ends, and you would put something on it, if you would calculate it as a beam, the bending would destroy the string. It just elongates like crazy by deflecting downward. This elongation causes tension, and this is how it stays in place. So nonlinear geometry is the effect that makes this happen, because linear geometry would like to treat the string as a beam, because what it's blind to, it doesn't see that as the string deflects, it has to elongate, and this elongation is not for free. You actually generate tensile force by elongating the string. And linear analysis just don't see that. So it can easily display, if you have like 10-meter string and apply a load to it in linear FEA, you can get like 20 kilometers of deflection easily, right? The problem is that you can't really deflect 10-meter string into 20 kilometer length, because that's kind of too much. And this effect is nonlinear geometry. It's very subtle, because in many analyses, that's completely not an issue. If you're designing a car engine, and it's like a bulky, heavy thing with thick walls, there's nothing that nonlinear geometry will do there. You can toggle it on, toggle it off, you wouldn't notice the difference in outcomes. Because things have to be relatively thin. It's called slender technically, because it's not about how thin the plate is, but rather how thin in relation to its length it is. So if things are slender, then nonlinear geometry will play a role. And the more slender they are, the bigger the role will be. And so that would be it. And you can actually not expect this if you never encountered this in like your previous experiences. If you get stresses higher than yield, you instantly know that something's wrong. You can calculate things which should be calculated with nonlinear geometry without it. And like there is nothing on your screen that indicates that something went wrong. And there are serious issues associated with that. So that would be one. The second one.
Let me
would
just
be nonlinear
quickly
material.
push in on that. Nonlinear geometry, I always thought of it like if you have a bending lever, and the action, the point where the force is acting is changing with the bending of the lever. That changes the lever.
Yeah, that would be.
That's the same thing?
This would be a kind of nonlinear geometry.
Yeah.
Although to me, it's a kind that's very unintuitive. I would have a problem of like mentally associating this. This is why I'm using a string, because it's like a real life thing, like a string in a bow, right? But yeah, that would be nonlinear geometry.
But it's
too.
the same thing. You're changing the point.
As it bends, you kind of move the force closer, and it kind of changes, right?
Yeah, the moment gets smaller because the bending, the force is traveling towards the support, right? But with the string, I didn't get it quite. So you meant with a string on both ends, and then you pull in the middle?
Let me, I will actually use a prop.
Okay.
I have a string here.
Yeah.
Right? Well, it's a cable, actually.
Yeah.
If I put it, if I keep it in my two hands.
Yes.
And I would weight something here, like a 1 kilogram of water or whatever.
Yeah.
What would happen is it would go down like this. It's actually like I should have had a red string maybe.
Yeah.
And the problem is that if my hands don't move closer together.
No, I get it. Yeah.
It's like if it's straight, it's the shortest path between this support and this support.
Yes.
And as it bends, it has to get longer. And it gets longer by generating a tensile force.
Yes,
and it's actually this tensile force that resists the bending, not the bending in the string. Because if you would calculate the bending stress, treating it as a beam, it's destroyed even if you think about it. You don't have to even load it.
Yeah, right.
The capacity is minuscule at best.
All right, understood.
So but that would be the same effect, really.
Yeah.
Like how the sails in a ship work. You have the horizontal beam on the top, horizontal at the bottom. There is like a cloth.
Yeah.
And when the wind blows on it, if you would calculate this cloth as a beam, the bending capacity of it is non-existent.
It's nothing,
And yet somehow it didn't break. That's the nonlinear
because of the
geometry.
tensile,
But it also can happen that if you have those two beams in a ship and the wind blows very heavily, they can go like squash together because there is a stabilizing force generated by this effect. And that's how nonlinear geometry can catch you off guard. You might not expect this, right?
Yeah.
So that would be one. And I usually start with this one because it's the difficult one. The easier one is when you have material nonlinearity. So very rarely you get a nice linear relationship between stress and strain in material. It's usually
not for long
in some way.
With a low load.
For long. Exactly. At the beginning, everything's fine, and then it really goes badly, right? So that would be nonlinear material is complicated in a sense in how to understand outcomes and stuff like that. But when it comes to the idea, it's very simple. You just tell your solver, look, I'm using this material. The actual relation between stress and strain in my material looks like this. Please take that into account into analysis, press play, and it does it. So if the material yields, for instance, you can't have stresses higher than yield because the yielding plastic redistribution of stress will just push the stress somewhere else. And you get a certain level of reality into the outcomes that linear analysis just can't give you.
Yeah. But harder conversions.
So that would be
so it's better result, but it's also harder to achieve, which is somewhat fair.
Yes, absolutely.
Yeah.
If we would like to compare, linear analysis of a big model will take 5 minutes. Computing on nonlinear geometry and nonlinear material will take you 2 hours.
Yes.
So it's not for free.
Yeah.
There is cost associated with it.
Yeah, definitely.
But you don't really have to think about outcomes then, because you look at them and say, oh, that's acceptable or not. You don't have to convince anybody that ignoring this much of this particular place is still okay because you said so.
Yeah.
There are actual rules that you can follow that will make this so much easier.
What I experienced with that was that you shift your attention away from the stresses, because with nonlinear analysis you don't have higher stresses than yield. But then you talk about the strains and how much strain is acceptable, right? Is it 1%? Is it 2? Is it 5? Depends on the material and stuff. So you have a different kind of discussion, but you will still have this discussion. But yeah, for sure.
But although the better thing is here, Manuel, the beauty of it is that when you know the stress-strain relation of your material, you can actually know compare, how much strain you can accept. So there is
it's a simple
an
relation.
Actual limit. And what's even better, the codes and standards for design will often tell you can't we don't allow plastic strains higher than this much for this grade of material.
Yeah.
So
This
you
makes
can
a
say,
lot
according
easier.
to the code, the strains are acceptable, everything's fine. And you don't have to convince anybody that if this is a good idea or not.
Right.
It's just there.
It's just on paper.
Right?
Yeah.
You can
Yeah.
say the capacity is at 89%.
Yeah.
Because there are digits you can use to compute
Yes.
the value
Yes.
rather than, oh, I don't know what is the capacity ratio. Because every time someone argues, can I ignore this much stress?
Yeah.
My first question is, can it be 1 megapascal higher? What about 2? 5? 10?
Yeah, you're playing
Like,
devil's
where's the
advocate
limit,
here.
right? And there is none.
Yeah. Yeah.
So
You cannot know it
that's
precisely.
the beauty of it. Yeah, exactly. And since you asked about
Yeah.
types of nonlinearity,
Yes.
I guess that we get to the orphan in the crowd, and that would be contact.
Yeah.
Because I'm not really
Tell me
certain
about it.
if I have the guts to publicly call it nonlinear, because this would be like a very awkward discussion, because it's a fact that you, in some solvers, depending on how they have their user interface written,
Yes.
you could run a linear analysis with contact, which would make it a linear contact, and then nonlinear analysis with contact would be a nonlinear contact, or does the contact has to change to be linear or nonlinear? Nobody knows. The reality of contact is that if you have two elements in your model
Yeah.
and they can touch,
Yes.
sometimes they will,
Yeah.
sometimes they won't,
That's
sometimes they will
nonlinear.
partially.
That's nonlinear.
Yeah.
Right?
Well,
Just because some solver names it differently.
I'm not having this discussion.
Okay. For me, it's nonlinear, clearly. So if the contact is
For
not
me,
frozen.
it's just two things touching. Whether you like to call it linear or nonlinear
Okay.
doesn't matter.
Okay.
Because in the end, the effect is that two things can touch. And depending on the load, something can change in how they are touching. So clearly an iterative process, even in a linear analysis, if you have contact, there is an iterational process involved to see what is touching and what is not.
Yeah, let me propose it. One sentence with that. Whenever you're changing the stiffness matrix between one iteration and the next, it's nonlinear. And with contact, you do that. Because you update the stiffness matrix. Because the model has different... Right? Yeah, okay.
I have nothing against that, Manu.
Okay,
Like, seriously, I don't oppose it in any way.
Okay.
The thing is that there is always a discussion, and then someone says, no, we'll do linear analysis with linear contact.
Okay.
And then you're like, no, it's not nonlinear, but the solver is linear. Like, you
Okay,
can buy a
okay,
linear
okay.
solver bundle
Yeah,
that
sure.
does solve contact, right?
Okay, yeah.
It becomes beautifully complicated, not on a level what is true, but what people call it. And
Yeah, right,
I think that
it's different
what
tribes
is more
then.
important is not the name,
Yes.
the name itself.
Yeah.
What's important is actually what the thing does. And whether you're doing linear analysis or not, if two things can touch, you will have contact. And
Yes.
contact is, to me as a structural engineer, contact is not a very complicated thing.
No.
Because you can have friction or not.
Yeah.
Like in a very waste scenario, you can have a kinetic friction. If you want to see how much force you need to start pushing something and then pushing it along, starting is more difficult because you have static friction, and then pushing it along is easier because of kinetic friction.
Yeah.
That would be as complex as you can get. But
Yeah,
if I would be a mechanical engineer designing braking systems in a car, suddenly the friction making the thing stops causes heat. And this heat is caused by the friction on the moving part. And this will become highly complicated in this regard. Right?
Yeah.
So to me, contact is simple. I see that it can be way more difficult than what I use in my work, simply put. But this way or another, it's just an art of two things touching together in analysis. And that would be something, right? And it's good to remember that if two things are touching, connecting them might be a mistake. Because if a book is lying on the table, it's not welded to the table.
Right,
You can pick it up.
Frozen contact.
Like, sure, if you push it against the table, it seems welded, right?
Yeah.
If you try to lift it up, it's very easy. So just modeling things as welded because they are touching
it's a
very
difficult
often
thing.
misleading.
Yeah. And also a highly made beginner mistake, I would say. So with contact, I mean, contact is not a hard part to understand or so, but I mean, there are different types of modeling it and stuff, and you can very get very complex in whatever penalties and augmented Lagrange and whatever. But in the end, you just have to make sure that your contact works as expected.
Yeah.
And
Yeah.
you have to make that sure. Not just your contact standard and go
and
with
then
it.
that it converges.
Yes.
Because contacts are notoriously terrible to converge. It's
right.
like I think that it's the most irritating part of
it is.
Even if we'd agree to call the contact non-linear, the contacts that would be the most irritating part of nonlinearities, because converging contact
it's
sometimes
hard.
in some circumstances
could be hard.
Is a freaking nightmare.
Right. Yeah. And also make sure that the penetrations is not too large with contacts, because you could have it converged, but then it's penetrating like crazy, like multiple millimeters and stuff like that. Then it's also not really a thing.
Yeah. Well, I think that luckily, I'm like definitely in FEMA, but I think in most solvers the compliance by default is like 0, so it assumes that you just can't penetrate. So you have to actively set the possibility for things to fall through, and then the assumption is that you did it, so you'll pay attention to it. So it can't catch you off guard. You were setting this up at the beginning, right?
Yes.
But yeah, that's true. And if you're transferring load with friction, friction is one of those things that only happen when you don't need it. So you have to be very careful, like how much are you really pressing and how much friction do you really have, because it's like I usually assume that friction is only there if it hurts. Like if you're happy with friction, you shouldn't consider it.
Right.
But yeah, that would be it. And
that would be contact, big topic. Maybe we can also talk a little bit more if you have the guts to open the discussion again. No, I really was not aware of that it's such a big thing. I thought, well, contact nonlinear, everybody agrees, but I learned something new today.
And to be honest with you, I don't care. But I've been a scientist for 10 years. And those scientific discussions, whether or not something should be qualified as something, are terrible.
That's tiring.
You could write most likely you would be able to write a PhD whether a contact should be linear or not. Right? And to me, it's just semantics. There is, whether we call contact linear or not, has no impact on anything that I do.
Yeah, you have just to understand contact as it is.
Yeah, but still, there would be scientists arguing this way or another.
Right. Yeah.
Because
we are both beyond that point in our career.
Luckily.
All right. Let's go to the.
Let's call it half nonlinear.
Half nonlinear. All right. I will research that a little bit because it made me curious. Never heard about it, but yeah. Let's move on to the second half of our picture here. We have this modal analysis, right? So no vibration and forced response. So let me tell you what I encountered in my career until now. I know modal for sure, eigenvalues and stuff like that, frequencies. But then also you have this frequency response analysis where you have different kind of sine waves you put on the structure and see what the response you're getting.
Yeah, that would be forced response to me.
Yeah, all right, okay. That's PSD, I think it's also called, right? PSD analysis? I don't know. No, not entirely sure. I'm just learning this stuff a little bit more as we're speaking. And there's this g² per hertz curve you have as an input function and stuff like that. Have you heard of that? Yeah.
No, I don't do dynamic analysis that often.
Okay.
So I can tell you what I know, because this is often used in earthquake designs of very complex things when you have force response.
Yes.
And there are softwares that actually have input from earthquake as an input file.
Yeah.
So you can model whatever you have and literally make an earthquake that was in San Francisco in 76.
Yeah, and see how they propagate.
And there are different, depending on the region, there are different earthquakes that are the classical choice, right?
Yeah.
So I'm not designing things like that, luckily. But but that would be, to me, that would be it, right? But I think that to dial it down to the basics first, well, it's quite obvious that when you do linear analysis, you don't do any sort of vibration analysis at all. Yeah. And if something could vibrate, it could potentially fail due to vibration, be it fatigue or resonance, it could be both in some sense, but let's leave this aside. The idea is that you have to analyze it, so you want to know if your thing will shake. And it's something akin to stability, really, that if you're not expecting it, it will catch you off guard. You can do your linear, static, or even nonlinear analysis and be, a happy camper. You just don't know it, right?
Yes.
And then the model analysis would be a perfect equivalent to linear buckling analysis.
Yes.
It doesn't solve anything really, it just shows you things. So what I mean by this is that model analysis will show you the frequency and what shakes and how big percentage of the mass of whatever you have modeled shakes.
Yes.
Right? And the idea here you would do is, I hope that when I do model analysis and I get those frequencies for my structure, the frequency of the load I think I will have, let's say that you have a machine that vibrates with certain frequency and you're afraid that it will start to shake your entire building, right? You just hope that the frequency of the machine and the frequency on the building do not match.
Yes.
And it doesn't have to be a perfect match, let's say 10% from one side, from another side, you want to be clear.
It's bad enough.
Right?
Yeah.
And then if you manage to land something like this, you're kind of okay. This rarely happens though, because normally structures have a lot of model frequencies.
Yeah, right.
You just have the first one, and if you happen to have a load that is lower than the first one, you're happy, right?
Yeah.
But if the load frequency is higher than the first one, there might be 76th model pattern that will perfectly hit your load.
Yeah, right.
Of course, one can argue, okay, but maybe the 76th model pattern only includes a handrail on a 7th floor somewhere near the stairs.
Yeah.
Right?
So if that
And
breaks,
then you think,
not
okay,
because
let's
of problem.
build the thing, and then we'll just dampen this particular handrail.
Yeah.
Right? The problem with model analysis or even forced response analysis, as far as I understand it, and I talked with people who do it, is that it's extremely difficult to make a model that represents your structure dynamically well enough to believe in outcomes you receive. Because when you do static, so no vibrations whatsoever, if you have a bolted connection, it doesn't really matter if the bolts are super tightly screwed or maybe a bit loose. From static point of view, as soon as the tension will appear in a bolt, it will start transferring the force. And if it's super loose, maybe the plates will open a bit, and instead of super rigid connection, you have slightly less rigid connection. But usually rigid connections are pre-stressed anyway, right?
Yes.
And if not, you'll be assuming a hinge anyway, so that would literally not change much, right? So for static, that works perfectly. For dynamic analysis, the same situation would be two completely different problems.
Right.
And suddenly you're trying to assess how this structure will be executed, well, the problems in erection and montage and whatever they are doing on site, what will go wrong, to take that into account. That's an impossible challenge. So in the
it's
end,
pretty hard.
you have something like an ideal model and imperfections for dynamic analysis would be crazily more complicated than for buckling analysis. Because for buckling, you need just the shape that kind of follows how the thing will buckle.
That's more or less easy.
Imagine that even if you would just bend the sticks and look at them, you could kind of imagine how this will look in real life.
Yes.
When it comes to dynamics, everything takes part. And suddenly, you may not have modeled things that will be important in your analysis, the model analysis, right? And then you're doing the model analysis and essentially hoping that your model is good enough.
Yeah.
And I have a friend who has a PhD in dynamics, and I asked him once, what would be the best approach? And he would say, build it and then dampen whatever shakes. Because it's so difficult to build a model that would represent the structure sufficiently accurately to actually see what would be the problem. Of course, if you have a huge structure and everything is butt welded, you know the rigidity of every connection, you can model everything, and that's simple. But as soon as you start bolting things, there are secondary elements, cladding and whatnot, it becomes so beautifully complicated that the outcomes will be tricky to analyze.
Because
I think that would be the big drawback.
Yes, because everything which interferes with the stiffness of the structure takes largely into will be taken largely into account with the analysis.
Or mass. Because
mass
you can
and
have
stiffness,
mass
right,
without stiffness, and that would interfere too. Right?
Yeah, right.
And then the rigidity of things is way more important when vibrations are concerned.
So pre-tensional
the things
stuff
that you
is
would normally ignore in static may actually start shaking, and you don't even have them in your model.
right.
Okay. So that's the beauty.
That's beautiful, complex. But I think, there's different approaches to it, right? So you could also just use modal analysis just for noise, vibration, and stuff that you see that you don't have any frequencies which you would hear in a car or something like that. But for failure, that's hard to get. Yeah, and it's a whole different topic.
To this end, I think that the difference between modal analysis and force response would be something like this. Let's say that I have a machine that has 4 hertz of load frequency.
Yes.
And the first model of my structure is 3 hertz and the second is 5 hertz. So clearly my machine is somewhere in between of the first and the second model.
Yeah.
Like the numbers are crazy. This will never happen in real life. Those things are way much closer together. But let's say that would be it, right? And then the question is, okay, the modal analysis showed that the resonance as uncontrolled higher and higher amplitude of shaking until failure most likely would not happen.
Yes.
But what will happen? And modal analysis doesn't answer this. It just says the natural frequency of your structure, the first one is this much, the second one is this much, that's it. Right? And force response would kind of allow you to record the vibration of whatever you have, apply it to your structure, and see how the structure would behave.
Yeah.
So that would be like a way more advanced way of approaching this. This is why you can have like a recording of an earthquake. Right? You just apply to foundations and see what happens. That would be kind of the idea there. You can also see how 2 machines with different frequencies would interfere on the same floor on the factory. Or things of this nature could be analyzed. And but the problem remains, like the accuracy of modeling with dynamic analysis would be very, very difficult, and you have to very pay attention to it, as far as I know, at least. So,
that's the same thing,
so
but you have
difficulty here. I think.
With the modal, you just use that if you don't have any idea or not a very precise idea of what frequencies your structures will see. And if you know perfectly well that you have this machine emitting this frequency and you have another machine emitting another frequency, then you use the force response to just check for those sources of frequencies you have. And so you can also a little bit boil down which model to use. All right.
Yeah, that would be perfectly. Yeah, that would be. But still being careful about what you assume in your models, whether the connections are tight or not. Those would be the things that can make or break your analysis, really. And to me, as a structural engineer, that's a scary concept. Because I fully know that you won't, when you're doing the design, you wouldn't really be able to...
You cannot tell.
To see how this works.
Right. Yeah,
you just can't.
Yeah.
And for imperfections, when it comes to buckling, there are rules. Vague as they are, there are rules that would allow you to
have a guideline,
guesstimate what the imperfections might be.
Right.
Here, you are on your own, and this is more important. So it's a difficult thing.
So if you're close, better build it and test it. So, but I think that's a good tip.
Tell this to the guy who's designing the skyscraper. Right?
I think that's a good. For a skyscraper, that's maybe not possible, but. For smaller projects, I think that's a great advice to just build it and test it and see where it shakes. I mean, that's perfectly pragmatic. I just like the solution.
I feel that you could do like firstly do the dynamic analysis of some sort, then build it and see how much off you were.
Yeah.
And then try to gain experience from that. And I think that it comes down to just like with imperfections, it goes down to the experience in a particular branch of engineering that you're involved with, and the experience tells you what to do more or less, right?
Yeah.
So it would be just more difficult to get the dynamic experience, I feel, or at least it depends on what you're doing your PhD in and things of this nature. Which books do you read? Right?
Yeah, sure.
I'm just in love with stability, so vibrations were never like this. I was never this close.
Yeah, right. Okay, last part is inertia effects, right? And implicit and explicit, that's more or less a formulation of the model or the solver, I would say. And inertia effects, that's kind of a different nonlinearity, but something...
Oh,
it changes.
Maybe.
With time.
Yeah,
so,
okay. Look, Manuel, if this makes
I'm an
you
easy
feel
guy
any
with that.
better about our conversations, you have it.
All right.
It's a nonlinear.
Yeah, we could also say it's neither of those, but it's a source of change. Let's say that. It's a source of change.
Exactly. I would say that it's a choice, whether you want or don't want to have this in your model.
Yes.
And will we call it, does it formally is a nonlinearity or not? I don't care. Because there is no impact to it. But
you could call
we can
something
joke
different.
around this for however long we like. Right? To me, inertia effect is just a thing that if you swing a fishing rod in real life, if you do it fast enough, you will actually bend the rod by the act of swinging it.
Yes.
And you can do whatever nonlinear geometrical analysis you like. There's nothing like this. It will, if you would apply a rotation at light speed to the tip, it will just nicely rotate like this. Nothing would wobble, nothing would shake. It would be like plain, nice rotation. And inertia effect basically does this. That things, as you start to move them quickly, they react with inertia. And you can have that in your model. And funny enough, to me, that would be the real dynamic analysis, where time is involved and inertia. Like that would be the dynamic analysis. Because vibrations would be still considered dynamic analysis, right? But you can do model analysis and time is not involved. Like you have outputs in hertz, so let's say that seconds were somewhere around. But
but it's more or less a function,
essentially,
not really a...
Yes, exactly.
The real thing.
But here, the time is needed in your analysis.
Yes, in solving.
On its own.
Yes.
You will iterate the process through time.
Yes.
To see what happens, and that would be the true dynamic analysis.
Yeah.
And it's cool.
Yeah, definitely. So
really
you did also some transient analysis in your career.
Oh, what's transient? Because this word appears so many times, and like...
For me, it's if you have time in your model. That's an easy thing.
Okay, because you know that this is like I was never good with semantics of things, especially since we both translate things from our language to English as we talk.
Yeah.
So it makes things complicated. But yeah, totally. I did like we do from time to time, not very often, but we do implicit analysis. Explicit, not really. But like implicit would be called slow dynamics, maybe.
Yeah.
So when something happens in time, I had situations where something was pushed and we needed to like have static friction, kinetic friction, see how this will behave. You will do that in dynamic analysis because you want to see how this will be
does
done.
in real
We're
life.
not doing like crash test analysis, but analysis where the time would be important. That's doable, especially since advanced nonlinear solver in FEMAP that I'm using would use time either way. Whether you do static analysis or like transient analysis, the time will be there in your model. It will just take or not take inertia effects into account on the click. So you can say, let's do, even if I say I want nonlinear static, it would still ask me to define time just to iterate the load through like linear.
But this has, with the implicit thing, time has no physical meaning in this case, right? So you have just your load application.
In implicit, I would say it does have. But I could have something like, looking like implicit analysis, but with time that doesn't have any physical meaning. It's just dummy time. It's just
it's
a way for the solver to know what load should be applied at which situation.
Yeah.
Let's say not moment, right?
Yeah.
And in implicit, like the actual implicit analysis, you have like a real time in real seconds, and you can play animation in real time to see how this will behave. And explicit just makes this very, very fast.
Yeah, I have to learn a little bit more about those two. I'm either confusing them all the time, but I thought that explicit is like you look forward in time, you have your current system, and then you just calculating gradients, and then you just go one time step in further, and then just calculate it again. And in implicit, you have more the integral approach, but I'm not 100% sure.
So I would compare implicit analysis to advanced nonlinear static analysis. The idea is that you have time steps. So both implicit and explicit use time. And you have a time domain, which means that my model starts at time 0, ends at time whatever many seconds, milliseconds, whatnot. And you have this, right? And in implicit analysis, you as a user can define what is the time step. So you can say, I want to analyze 1 hour of my model behavior, and I will iterate 1 minute at a time. And something is happening slowly in your model, and implicit solver will check, like compute the answer for 1 minute, and then iterate to compute the answer on a second minute, and check if the convergence is met. So it will basically do the same thing what nonlinear solver in static would do. There will be like increments, iterations, and convergence checks that in the end would allow you to iterate through the problem on the time increment you as the user defined. And the drawback here is that you need to check for convergence and do all the iterations and stuff like that, which takes a lot of time. But the benefit is you as a user can actually define the time increment. So you could actually calculate a process that takes 1 hour to finish. Because in explicit, it only really works in situations where time is super, super quick.
Yes, for small amounts, right?
You can't define the time step. The time step will be computed. It's effectively this.
Depending on your element size.
The impact wave will travel through the material on the length of the shortest distance of your finite element. So you have very small elements. The smallest may have like 10 millimeters across on 1 millimeter. And then the impact wave traveling like few thousand meters per second. How much time does it need to fly through there? And this is the time increment. So it would be like 1 times
maximum,
10 up to minus 7 or minus 8. So like the time is super small. So if you think about computing explicit of something that takes an hour,
it
will never finish. This is not how it works. Of course, you don't check convergence, and it kind of like does the mathematics different way. So each step is super, super quick. But you need to have a lot of those to get anywhere. So this is more or less reserved to super quick things that happen in very, very short time. If you shoot a sniper rifle and the bullet flies and hits something, that's very quick impact. So that would be a very nice explicit problem. But if you have a longer time, implicit solver with your time step definition is needed, because while you will waste time to converge each step, at least you will get somewhere at the end.
If you converge.
So that would be the difference.
All right.
If converge, of course. Like you can have a lot of problems along the way.
Explicit. It's easier to converge, but you have to make sure that you have a very small time.
If you've been working with nonlinear static solver with contact, and you were fighting to converge each analysis for like 5 years, and then someone shows you an explicit solver and says, look, I'm doing like this, press play. It literally looks like cheating. Like if you would have some sort of cheating codes for FEA and suddenly everything converges at once because there is no problem. And it just happens like that. Although the problem is that the fact that you run explicit analysis doesn't necessarily mean that the outcomes have any sense. You need to be extra careful what you've got because
saw that too.
Overdo mass scaling or something like that. You can get to very weird places very quickly.
That's right. All right, I think that's all for today, folks. Yeah, was a pleasure talking to you again. Maybe
oh man,
we will...
it's always a pleasure to be here and talk with you, man.
Yeah, I mean,
really
I feel
have
the
to do
same.
this
It's
more often.
yeah,
so
we have
much
to
fun.
do that. Yeah, definitely. And yeah, I mean, there's so much more. We did not really go into the details of the dynamic, and we could do so much more about, I don't know, heat transfer and whatnot. But let's save that for another time. For now, thanks again for being here. Thanks, guys, for watching. Please comment,
Thanks for
like,
watching.
subscribe. And yeah, see you next time. Bye, guys.
Yeah, have a wonderful day. Take care.